तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Okay, we have been talking about minimization of Boolean functions, first by Boolean algebra, using Boolean algebra, and then used by corner map method, by drawing a graphical representation of the truth table and identifying the patterns of ones, and group them and reduce the variables in that process, number of variables as well as the number of terms. We also talked about, if you remember, we also talked about min term and max terms, min terms and max terms. That is, you can write an expression Boolean algebra either as a sum of products or product of sums. That is, and terms combined with an OR gate, or terms combined with an AND gate. So one is called the sum of products, the other is called product of sums, because in analogous to the algebra, one looks like a series of terms, product terms, and you sum them. Other looks like a series of sum terms, you multiply these sum terms as a product. Sometimes what happens when you draw a corner map to simplify, you find there are more ones than zeros. The idea is to minimize, we said, number of terms, total number of terms should be as small as possible, and the number of literals in each of these terms should be as few as possible. So when you have large number of ones, you have large groups of ones, results in many prime implicants and essential prime implicants. If there are more ones than zeros, is it possible to use the zeros and get the f0, f bar, complement of f expression? Because when the 1 in the truth table says the f is true, the function is true, 0 in the truth table says the function is false. So when you group zeros, we can get an f bar expression, just as we get f expression by grouping ones. And once I have f bar, I have De Morgan's theorem to get an f. So that is one approach some people use. That also depends on the type of gates you want. That all depends on whether you want a sum of product as the minimum expression or the product of sum as the minimum expression. So let us today see an example where we will use zeros to simplify the logic function. We will use our same familiar example from the last few classes. We have been using the function f is equal to A R B C bar. This has been our example. So when you drew the corner map for this, if you remember, this is the K map for where there is a 1 here, a 1 here, 1 here, 1 here, 1 here, 1 here. If you look at the truth table, we had one entry in the third row and last 4 rows. The first row, second row and the fourth rows had 0 in the output. All the rows are 1 in the output. Since we have done it so many times, I don't want to do it again, spend time on it. And if we map it, this is what we got. Is that right? All of you remember this? Yes? So now what we did last time was to simplify this using 1 here and then here. Of course, this is a trivial example. You will find even though there are a number of ones, large number of ones, if they are properly formed and the pattern is good, large groups of 1 together, it will give you a very small sum of product expression, because larger and larger groups of 1 gives you smaller and smaller product terms. That way we had a nice example. This example had A for this and BC bar. But just to give you the illustration, the example, the concept of using zeros to simplify the expression, I am going to fill these entries of the truth table which had output false with zeros. I am going to use zeros to simplify my logic function. So if I group these ones and write prime implicants, I will get F expression for the output F. If I now group these zeros and identify prime implicants and essential prime implicants, I will get F bar. Is it not? Whenever the function is not true, there is a 0 entry in the truth table, in the truth table as well as in the corner map. So now I am going to group these two zeros and these two zeros. So I will call this 1 prime implicant 1, prime implicant 2. F bar is sum of prime implicant 1 and sum of prime implicant 2, or combination of prime implicant 1 and prime implicant 2. When you say sum, you mean really OR operation. So which is 1 is what? This is A bar, B bar. Correct? This is A bar, B bar. This is A bar, C. A bar, C. But this is only F bar. But we want F, and we want, because the problem definition or the truth table given to you is to implement a function F which had the output asserted as true for the given combinations. But what we got is F bar, output not asserted or output asserted 0. So we don't want this, we want complement of this. So we want a complement of this. You know how to get the complement? By taking De Morgan's theorem on both sides, applying De Morgan's theorem on both sides. You get F is which is nothing but A or B, because the variable gets changed into complement, and becomes or becomes and, variable gets complemented, and you can simplify this to original F, which is A plus BC bar, because now if I do this, this will become A, AB, AC bar, BC bar. We have the identity in the Boolean algebra, if you remember, A or AB is A, correct? So this is redundant. Similarly, AR A bar, AC bar, also A. This combined with this will give you A. So these two terms get knocked off. So the result is A plus BC bar, which is what this is. The point I am trying to make is here a couple of points really. One is a smaller number of ones, grouping is easier only if they are randomly situated actually. When ones are nicely grouped, you may find a good simplified expression minimum form. But if you had ones and zeros spread in a random fashion and more zeros than ones and more ones than zeros, maybe it's a good idea to go for a simplification using zeros. The second thing is, this is the expression for f without this simplification. This simplification I did to prove that this is same as this. I can stop here. This is the minimum product of sum in the product of sum form. This is a sum of product expression. This is a product of sum expression. So if I wanted the solution in the product of some expression, want the solution in the product of some form, I would stop here and use this expression, the minimum product of sum. This is a minimum sum of, just as you get a minimum sum of product expression using corner map, I will also get a minimum product of some expression using corner map, using zeros. Where will I use that situation? I will use the situation where I want to have OR gates feeding into an AND gate, because here there will be each sum term is an AND gate, each product term is an AND gate, and a sum term represents an OR gate. Sum is equal to OR. Now, really no sum, it's an OR operator. Because we put a plus, we call it sum. Plus is an OR operation, dot is an AND operation. So, sum term represents an OR gate, a product term represents an AND gate. So, if you want to have fewer OR gates and larger number of AND gates, I will use a sum of product expression. Or if I have fewer AND gates and larger number of OR gates, I will use this. So depending on the topology, as they call it, depending on the topology, I will have either a sum of product expression or product of sum expression, even if the number of zeros are more or less, even without considering the number of zeros or ones in the truth table, or regardless of zeros or ones distribution in the truth table or the corner map, we may sometime want to write the expression as a product of some expression. In that case, I will use this approach. I will group zeros together and get f bar and then f. But you can do one more thing. You can skip this by reading judiciously, because A or B correspond to this. You will read it, because this I can do it mentally. Writing A bar and B bar and taking its complement, knocking off the bars here and removing this and putting an R, all this can be done in my mind. I can see that whenever two zeros are together, this is A bar and this is B bar, I can write this as, instead of A bar I will use A, I will use an R symbol, this is B. That means I will read the map as if I would read a product term. I will read a sum term as I would read a product term, except that I will remember to complement each variable and remember to complement each operation. AND operation will be written as OR operations and variables will be written as its complement. So without going through these two steps, which is of course not necessary, but I am saying I am not doing something which is wrong. I am just trying to simplify my procedure, visualize a procedure such that these two things are mentally done in your mind. So you can directly read the map as this. Let us take one more example to prove this point. This time we will have a 4 variable map. Sigma m, the number of min terms which form the sum will be 1, 3, 4, 5, 9, 11, 14, 15. This is the map for F. I can use any variable. I'll call them A, B, C, D. So the variables for which the min-terms for which the output is 1 are true, or 1, which is this, 3, which is this, 4, 5, 8, 9, 10, 11, 12, 13, 14, 15. This is the distribution. So this is my prime implicant 1, essential prime implicant here, these two. So this one cannot be combined in either way. This is another essence. This is the most efficient way of combining, because this one has to be combined, so this has to be there. This one has to be combined, this has to be there. I could have combined this way, but it's not necessary because I already taken this one into account. And again, these 4 ones form a prime implicant. Now, this would be, what would this be? First term will be this, which is, pardon? V bar D, P bar D, or this one, A bar B, C bar, then this one, A, B, C. Simple. We have done this earlier, and map is simple to read. There is no ambiguity here in terms of non-essential prime implicants and all that. On the other hand, if I try to use my zeros in the truth table, F would be wherever there is a 1, all other terms have to be put in this. So you represent this as sum of products. This is a product of sum, so we will put a product which is a pi. M for capital M for max terms, small m for min terms. So max term, what are the max terms that will be there? Whatever term is not here will be a max term. So there will be 0, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13. So it happens that I equally chose, just not that, did not do it intentionally. I wanted to have a large number of ones and large number of zeros. So it happened, and I took this example, that exactly 8 ones and 8 zeros. So you could have proceeded either way. Proceeded sum of product way or product of sum way. If you had a specific reason to go for product of sum because you wanted to use AND gates fit into OR gate, I will have to do it sum of products. And if I want to have OR gates fit into AND gates, I should go for product of sums. But if you are not given a choice like that, if you are not given a condition, constraint like that, in this case there are 8 ones and 8 zeros, I can go either way, right? So I will now put the zeros here. I will draw another map here, same map, but in order to avoid cluttering of the map, I will redo it here. Zero, 0, So I can group these zeros into groups of 2 zeros or 4 zeros or 8 zeros, as the case may be, based on the case may be, based on the adjacency rule, and then try to read them. So these 4 zeros form a group. These 2 zeros form a group from implicant. These 2 form a group. So there are only 3 terms. And I can write F bar and then take a complement of that using De Morgan's identity or De Morgan's theorem, and then write the product of sum form. Or, as I told you just now a while ago, I can directly read the map for product of some expression by treating a variable as its complement. When you read it as a complement, any variable is read as its complement, and an AND operator is read as an OR operator, and vice versa. So this should be, these 4 ones would be B bar, D bar, if you want to write it as a sum of product. Since I want to write the product of sum, this will be B or D. So this will be B or D. Is that right? Is there anyone who doesn't understand what I am saying? You look at these 4 as you would do F1. The only difference is this will be read as B, D if you are grouping ones. When you are grouping zeros, B will be read as B bar, D will be read as D bar, and will be read as an OR. So instead of BD, I will say B bar or, instead of B bar and D bar, I will read it as B or D. That's it. That's a simple trick, if you want to call it. It's not a trick really. It's a procedure which is bypassing some of the logical steps. It is not as if it is a new concept or anything, or it's not a derivation you need to know, or this is how you get it. Couple of quick steps, we proved that the same as this. Here. So the next term would be this. It would be if these two were ones, I would read it as B, I would read it as B, A bar, B, C. Now I will read it as A or B bar or C bar. And finally this 2 ones, if there are ones that will be read as A, B, C bar, that will be read as A bar, B bar, C. There you go. This is your minimum product of sum. This is a minimum. This is as min terms, this is as max terms. This is as ones, this is 0. This will use AND gates feeding into an OR gate for the final output. This will use OR gate feeding into an AND gate for the final output. But both are identical. You have a choice of using this or that, or if you are given a constraint as use many AND gates, only one OR gate, you will use this. If you are asked to do many OR gates, many OR gates and only one AND gate, you will use this. If you can use many AND gates and only one OR gate, you will use this. Sometimes these restrictions come in the design because of the availability of parts, because of the matching with the other part of the circuitry you are designing, because you may want to have an inventory of type of parts of the same type for different designs and different implementations. There may be several reasons why you want to go for this or that. So now we are done with, I also told you the other day, how to do a 5 variable map, 6 variable map. We've done some length 4 variable maps, which is generally for conceptually that is good enough. We talked about implicants, prime implicants, essential prime implicants, non-essential prime implicants, how to use a non-essential prime implicant properly and all that. We'll have to now go to some examples of systems, small ones. We'll design, we'll think of some real examples, and instead of, so far I've been giving you min terms and max terms lists without any physical relationship, any physical correlation with anything. It's just arbitrary sum of products, arbitrary product of sums, arbitrary zeros and ones in the expression, or arbitrary ones and zeros in the truth table. Before we move on to that, I want to, before we move on to some practical examples or real life examples, I will want to give one more concept. It's a very simple concept. It's called a don't care condition. This is not the state you are in all the time. Don't care states, right? You don't really care about what happens. Now, what is a don't care state? I have a truth table here with 8 rows, or a map with 8 cells, a map with 16 cells, or a truth table with 16 rows. And we define for each of these rows or cells an output to be true or false, asserted to be 1 or 0. That means you are very clear what you want the output to be for each of the input combinations. Very clearly, because based on that condition you are designing a system or a circuit. On the other hand, I may have a system, a circuit which I am designing, I will define the output to be true for certain combinations of the inputs, and it has to be false for certain other combinations of the input, and there may be some combinations which are not covered in both the lists. I can give a list of combinations of the input. There are how many combinations are possible with 3 inputs? 8 combinations. Out of these 8 combinations, I will say definitely for certain combinations, let us say 3 combinations, the output has to be true, and for another 3 maybe the output has to be false. And then there are 2 combinations which are not defined. Means you may not define it for many reasons. These combinations may not occur in your system. These combinations may not occur, or these combinations may occur, but you don't worry too much about that. It can be 1 or 0. The output can be true or false, because it's not going to affect your processing in any way. So there are certain combinations in any system, any circuit, certain combinations of input for which you will not define the inputs. The inputs are undefined, need not be defined for practical reasons. The practical reasons could be such a combination of inputs may not occur in practice, or the practical reason could be such a combination of input, if it occurs, I really don't know, I don't really care what the output is, because that is not going to affect my processing in any way. Whatever is the reason, if you want to say there are certain combinations of the inputs for which I do not care, that's why it's called don't care states. I do not care what the output is. Such states are called don't care states. I'll give you a simple example. Suppose I want to count 4 using one hand, 5 fingers, one hand. I'll use only 4 fingers all the time. 5th finger will not be used. So I'll say, supposing I show you a 3 like this, you know it's 3. Or I put, let us say, how much? like this. This also 2, because these 4 are the fingers we will have to look at. I am not showing any whatever, right. But supposing I put 3 and this thumb also out. I always tell you that look at my 4 fingers and determine the condition. Okay, 3 or 2 or 1, 3, this 4, 3, 2, 1. This finger you don't even look at, I am saying this thumb, you don't even look at. But I may put it like this, I may put it like this, it doesn't matter, because this is not going to affect you. This is 1 or this is also 1, this is also 2, this is also 2. Right? This is an example. In like that I may have 4 inputs, out of which 3 combinations, 3 input or certain combinations of 4 inputs is going to affect my output. I will be worried about those. If it happens, I have to take some action. And certain other combinations, if it happens, I don't care. Nothing is going to happen. I don't have to take any action. So we can always say it's 0. We are only interested in a particular combination, certain combinations of the input giving an asserted 1, logical output 1. When that is the case, you can always say any other combination coming, the output can be 0. Then you are very safe, is it not? I don't want a false output. Whenever I have a condition for which the output is required to be 1, I need the output to be 1. If there is a mistake in that, I will be worried. But all other conditions, I want the output to be 0, whether they occur or not. That is one way of looking at it. Is that not? That is fair enough. There are 8 combinations, I told you, 3 combinations for which the output has to be 1. I am worried about that, I am concerned about this. 3 other combinations, I say 0, and other 2 I don't worry. I can always combine all these 3 plus 2, 5, and say for all other 5 combinations I can have the output. When I don't care about the output, what does it matter to you if the output is 0? Okay. So I can say for all other combinations other than these 3 for which I want 1, output is 0. I can do that. That means I will have more zeros, less 1s. Or I can say, since I don't care about the output, those 3 combinations for which I want the output to be 1, and those 2 combinations for which I don't care what the output is, all the 5 combinations I will always produce output of 1. I will make sure the 3 combinations for which the output should not be 0, should not be 1. I will make sure for those combinations the output will always be 0. That is also possible. It's a reasonable argument. Either, both are reasonable arguments. But if you so doing, I fix these don't care conditions, the states for which you really do not worry about the outputs, the conditions for which you do not worry about the outputs, you are fixing it as a 1 or a 0. When you put a 1 on a map, you have to cover it, you have to enclose it, write a term. On the other hand, you put a 0, my number of 1s on the map gets reduced. When the number of 1s on the map gets reduced, my expression becomes more difficult, my expression becomes more complex. Fewer 1s is longer terms, isn't it? In terms of each term, you will have more literals, if the number of 1s is 1. So I would like to use these conditions for which I don't worry about the outputs to my advantage. Whenever I like, I will use them as 1 in order to simplify my hardware. But I don't have to produce a 1, so whenever I do not, it's not convenient to me, I will ditch it and use it as a 0. The advantage of this is, I can use this don't care condition to simplify my hardware. If I can put an extra 1 in my, for example, I had a 3 1s, group of 3 1s, if you put an extra 1, I will make a nice term. So there is a don't care there, a don't care in one of those cells, I will use it as a 1 to my advantage to reduce my hardware, may reduce my term. On the other hand, if I already completed all my 1s and there are some don't cares strewn around, I will not bother to cover them and write terms for it. So use it to your advantage. Don't care states are used to reduce the logic. Not necessary you have to use every one of them. Whichever don't care states are useful to introduction further Either the number of terms, or in a given term if you can reduce the number of variables. We call them literals. I said A, B, C, A, B bar, A bar, B bar, this is all literal. A bar and B bar are called literals. Each variable in a term is called literal, and each is a term. There are 2 terms with 2 literals each. 3 terms with 2 literals, 3 literals, 3 literals. So by using a don't care, if I can reduce this further, either the number of terms or a literal in any of those terms, then I will use it to my advantage, use it as a 1. Otherwise, I will not purposely go and introduce an extra term to cover a no term. No, don't care. I don't want to introduce a new term in order to include my don't care condition. It's an waste. So the idea is always to reduce the hardware, reduce the hardware, reduce the hardware. This is the theme, as I said in the beginning, the theme of this course, reduce, reduce, reduce hardware. Hardware reduction, which will result in power saving, cost saving, size saving, space saving, everything saving. That is why we want efficient hardware, but reliable hardware. You can't knock it off things arbitrarily and say it's reduced hardware. Use only 50% of the terms, I will have reduced hardware. But you will not get 50% of mark, you will get 0 marks. That's the problem. I say it's a digital course. So, either you get 0 marks or 1 mark. Is it right or wrong? So, reduction at what cost? Reduction without losing the reliability of the circuit. So, let us take an example of that class. I can use the same thing and put some don't cares. I will take, for example, the same sigma m for which the output are 1. What are the terms for which the output is 1? 1, 3, 4, 5, 9, 11, 14, 15. I don't want to change any of these. But instead of making all other terms as zeros, I will say maybe 6, 7, 8 and 10 are don't cares. How do I write it? D for don't care. Some people use X, some books use X there. Some books use, this D is replaced in some books by X, some books by phi, some books by capital D. It's all the same. Don't care. Don't care terms are, let us arbitrarily put that. Why not I put these 2, these 4, 2, 6, 7, 8, just to show the effect. I don't have an idea what it's going to look like. Just arbitrarily assuming from the list of zeros, I am arbitrarily assuming these 4 terms need not be really zeros. They need not be ones, they need not be zeros the output. They can be don't cares. You don't worry whether the output is a 1 or a 0 for these 4 conditions of input combinations. So my map gets modified with don't care. This is a modified map. Modified K map with don't care states. What are the terms for which there is 1 to start with? These are ones, these are ones, these are ones, these are ones. Is that right? Now I am going to add 2, 6, 7, 8. When I do 2, 6, 7, 8, I don't mark a 1 there. Remember, if I mark a 1 there, when I try to simplify this map, reduce this map, I will make an effort to include every possible one. That will be unnecessary waste of effort. So what I will do is I will have to use another symbol. If I put a 0 again, I will ignore them. If I put a 0, I will ignore it. If I put a 1, I will necessarily have to include it. So what I will do is use another symbol. I can use a D or X or phi, whatever this list. So let me use a D. 2, this is 2. Then what? 6, 4, 5, 6. 6, 7, 8. These 4 D's I have included to indicate the don't care conditions of those 4 combinations of input. These 4 combinations of inputs, when they occur, the output need not be 1, they need not be 0, they can be anything. It can be either 1 or 0, because that does not affect my circuit performance in any way, because I may not have those combinations of input at all to start with, or even if it does occur, doesn't matter to me what happens. Okay, if that is the case, then how do I simplify? Now I will have more options. I would probably do this as 1, 2, is that right? Or need not even have it. Oh, I can have these 4 and these 4. So this is my 1, this is my 2, this is my 3. Prime implicant 1, essential EPI. 1, 2 and 3, essential prime implicants. Now remember, look at this and see that this D has not been included, this D has not been included. So it's not mandatory. It is not necessary to include all D's. At the same time, I use D to my advantage. I use these 2 D's because they are advantageous. I am able to make a simpler grouping of these 2 D's. If I don't have these 2 D's, I would use this as 1 prime implicant, which will have 3 literals. Now I have a prime implicant which have only 2 literals. That means I am knocking off one of the inputs of my gate, AND gate. That's an advantage, hardware saving. So this is the concept of don't cares and how to use don't cares. So now let us write the expression. Once they are don't cares, when you combine them, don't worry, you don't have to keep them separate anymore. You can just write the expression as if you would write a normal expression, very same way as you write a normal expression. So 1 would be what? A bar B, good. 2 would be B C, good. And 3 would be D bar. Oh, this is B bar and D. Very nice. Now this is what we got now, including don't cares. Out of 4 don't cares, I will really use only 2. 2 have not used, because these 2 are to our advantage. Exploit them to reduce the hardware, but at the same time don't feel obliged to include every don't cares. It's going to be a burden to include every don't care, because it's going to unnecessarily give you more terms which are not required. If I want to combine this due to a D, I have to put one more term here, which is not necessary. This one is already covered. If you put a D here, I will have an extra term with 3 literals, which is a waste. One extra AND gate with 3 inputs, and an input. That input has to feed into an OR gate. That means OR gate input also has to be increased by 1. All those extra burden is not necessary. Same thing with this D. Now, originally we had this expression. We have now that expression. B bar D is same in both. These 2 terms have been introduced by each by 1 literal. These 2 AND gates will now have the modified form, only 2 inputs. Here I have 3 inputs. So that is the advantage in hardware. So I am having 3 AND gates feeding into an OR gate. I am not writing the values here. You know that this is A bar, so you have to come through A, an inverter, B is B, C, B, inverter. So you have 2 extra inverters have to be also included. This is the story of the don't cares. So now we have exhausted now all possibilities of simplification. Of course, shown you several things which solve an arbitrary in a random, not random, arbitrary. What I mean is sort of arbitrary examples we took. We didn't take any device or any, except in one case, I try to justify a plus b bars, a plus b bar, a plus b c bar, I said can have a combination. But justifying after we drew the circuit. But now we have to do the other way. We have to have a system. We have to have, like any system we want to design. What do you want from that system? For that system, you write the truth table. That is the design. You identify a physical device system that you want. How many inputs are there for the system? How many outputs are there for the system? What is the input-output relationship you want? And for the input-output relationship you want, you write the truth table. And from the truth table, you can either use Boolean algebra to simplify it, or go to corner map and simplify it. And you can do it a sum of product way or the product of some way, depending on the type of hardware realization you want at the end. So what we have to do is to take examples, simple examples of logic functions, arithmetic functions. This one interesting thing is in this course, we always been talking of logic gates. Logic means decision, right? True or false, or and or. For example, if this function is true, why is it called logic? Because the function is true if and only if both the inputs are true. All other cases the output is false. So we think of this as a logical statement. Logically we can, it makes sense logically. It's logical sense, it makes logical sense. OR gate is a logical gate. If at least one of the inputs is true, the output is true. Or an NOR gate will say the other way. NOR is complement of OR. Only with both the inputs are 0, the output is 1. All other cases the output is 0. So whatever. But then when we do, I said this all digital systems, many times it is computation also is there, computational intensive. If you remember, we talked about computers as the basic building blocks. Anything can be thought of as a computer. So the basic thing in a computer is an arithmetic circuit. Logic also comes occasionally, but mostly arithmetics. Add, subtract, multiply, divide. We will see that later on in this course, in the next few lectures, subsequent lectures. We can also build arithmetics using logic. Actually, logic gates, they are called logic gates, but we will use arithmetic circuits like AND circuit, OR circuit, add circuit, subtract circuit, and things like that, using this logic block. So logically, why is logic same as arithmetic? Because there are only two things. No? There are only. We are talking about binary here, binary variables. A variable which can only have two values, 0 or 1. So it doesn't matter if it's arithmetic or logic, because when I have two inputs, I want to add these two inputs, I want only one output is possible. Isn't it? An adder will have two inputs and one output, let us say. I want to add two numbers, binary numbers. Two binary numbers I want to add, I have two inputs and one output. And each of these two inputs can only have two values, and output can also have only two values. So if one of these inputs is, both the inputs are 0, the output is 0, you know that. Sum of two zeros is 0. If one of the inputs is 1, the output has to be 1, because one is a 1 and the other is a 0, the output is a 1, sum is a 1. So sum is 0 if both inputs are 0. Sum is 1 if one of the inputs is 1. What will happen if sum is 1 in both inputs? 1, 1 is the input. Both the inputs are 1, the sum of two ones is 2, and I can't represent 2, I can only represent 0 or 1. My output has to be what? 0. And I should also remember to include this another output called a carry output, which will know that when both inputs are 1, the output will be 0. Even though the output is 0, sum is 0, it results in a carry. So we will not know how to handle the carry. But that is the arithmetic part. What I am trying to say is, it's a logic function basically. I will have to look at the two values of the input, determine output, right? If the two values of the input gives me the output, so my logic gates can be used for arithmetic operations. So what we have done is the basic introduction to logic gates, introduction to Boolean algebra. We talked about min terms, max terms, sum of products, product of sum, corner map, simplification, don't get, etc. But then all of them will lead to, all of them will have to lead to the realization of things which we need. So in the subsequent classes we will take design examples from combinational logic, both logically and arithmetic, how we can build and design and build. That means you have to first design, specify a circuit, specify the inputs and outputs, and what is the relationship between input and output, represent form of truth table and use your tools that you have learnt, Boolean algebra or Karnaugh map, with or without don't care, sum product sum, all that. Finally come with a simplification, and that simplification will be what will be drawn in terms of true gates, and that gate circuit will work as a arithmetic circuit. So logic circuit will become an arithmetic circuit. We will see in subsequent lectures.